Alright, so yesterday we looked at section 1.1. For the rest of the week, we'll look at 2.1, which focuses on how we measure angles. Okay, all kinds of things we can do with angles. There's different ways to measure them. You're probably familiar a little bit with degrees. Well, there's another way we'll talk about. And then once we know how to measure angles, there's some different things we can talk about, like the length of an arc in a circle, the area of part of a circle, and then the last topic we'll look at is what's called angular velocity. It's basically the speed of something spinning, like RPMs. It's measuring how fast something is revolving per minute. So those are basically what we're going to look at the next 3 days. All right, so before we even really talk about how to measure an angle, I'm just going to define what an angle is. And I'm going to start by defining the parts of an angle. And one part of an angle it's the ray. Okay, so a ray is basically, it's a portion of a line. It has a starting point, goes on in one direction forever. Okay, and when we think of drawing an angle, it's really made up of two rays. So if we just had a single ray, it would look like that. Okay. Add another ray to it. Now you just created an angle. But the key is, notice where I drew the other ray? I didn't just draw it over here. Okay. I had to draw it so the rays had the same vertex. Okay, so if you put two rays together and they have the common vertex, that's when you created an angle. So if you're going to draw an angle all by itself, that's generally how you do it. Now, when we draw shapes, okay, like a triangle, we also call these three things that I just numbered, those are angles as well. Even though technically these aren't rays. When you draw a triangle, it's three line segments, right? So when you draw an angle inside a shape, it's usually not rays. When you draw an angle all by itself, it is. Okay. Any questions on that? Okay. So there's another example of an angle. So it's just two rays. Make it so they have a common starting point. There you go. And usually when we get into measuring an angle, or we're talking about how big an angle is, we're talking about this part. It's the going between the two rays, the short way. You can go the outside, okay, the long way, but usually we're interested in inside the rays, okay? Usually. So the two rays form the sides of the angle, and the sides have names. Okay? It's called the initial side and the terminal side. Does anybody know how you would tell in that picture up above which side is the initial side and which side is the terminal side? Anyone have a guess? Do you mind?
It's longer than the other.
Well, they're rays, right? So they both go on forever, right? Even though, I mean, I might not have drawn it perfect, but both of those have arrows, so they just keep going. But, no, it's a good guess. Any, yeah?
The side that starts the angles would be the bottom one, I'm guessing.
Yeah, in this case, this is the initial. And this is the terminal. And the way that you can really tell is if you start at a side and you go the short way, okay, you go basically counterclockwise. Okay, so that's a better way to explain it. Go counterclockwise from the initial side to the terminal side. Wherever you end up and finish, that's the terminal side. So if I drew something like this, I said you go in a counterclockwise direction, the short way, okay, between the two rays. That way. Okay, the initial side is this one, and the terminal side is that one. So that's how you can tell if it's not drawn a certain way. This one is easy to tell, and that's the way we usually want to draw an angle, and I'm going to talk more about that in a second. The one in red is kind of turned. It shouldn't, the initial side shouldn't be pointing up in the air like that. We usually like to keep the initial side horizontal. And then it makes it even easier to figure out which one the initial is. Okay. All right, so when we measure an angle, you can measure it in both directions. I've been using the term counterclockwise to describe how to get from the initial to the terminal, but clockwise is another way to measure an angle. Well, if you measure something counterclockwise, okay, that's a positive angle. So if you're measuring counterclockwise, you're measuring a positive angle. What do you think would happen if you measure clockwise? Kind of numerically, what kind of number do you think would indicate clockwise instead of counterclockwise? Ethan?
Negative.
Yeah, negative. So if when you measure, you're measuring in a clockwise direction, the angle would be negative. And I'll show you an example in a second. All right, so let's take a look at an interactive thing where I can move the terminal side. I can't move the initial side, but I can move the terminal side, and I can create different angles. So we said earlier that if we measure counterclockwise, that's positive. So that would be going in that direction. Okay, so initial side is always on the x-axis. I can't change it. But the terminal side, I can drag it wherever I want. Okay, and as I keep going, the angle just gets bigger and bigger, till finally the initial and terminal side get back to where they were, and now they're right on top of each other again. So without that red spiral, without this number, you couldn't tell the difference between what I have drawn there and what I have drawn there. Well, put it right on 0. Okay, they look exactly the same. What that means is when we start doing stuff with trig functions, like sine, cosine, and tangent, for trig purposes, the angle that's 0 degrees and the angle that's 360 degrees are exactly the same. There's no difference which one you use. Okay? Because the initial and terminal sides are in the exact same spot when you draw them. If you go more than 360, then we start getting angles that are bigger. Okay? Now we've gone more than one revolution. And to show someone you've gone more than one revolution, they usually draw that spiral. We don't get into drawing that a lot. Okay, so let's go back to 0. And now if I go in a clockwise direction, now I'm getting negative angles. So in this box in the lower right, it's measuring the angle. That top number, negative 133, that's degrees. Does anybody know what that bottom number is? Negative 2.32? Yep.
Minutes and seconds?
So that's a good guess. A lot of times you can use degrees, minutes, seconds to measure an angle. It's in our book, but we don't go over that. So there's another way to measure angles that doesn't use that. Yep.
Radians?
It's in radians. Okay, so that's what we're going to talk about later today. Okay, really important that we know how to change something between degrees and radians. So all the angles that I just drew on the screen here, this one with the initial and terminal side, okay, this one, all those angles that I'm drawing, they're all in what's called standard position. Okay. To draw an angle in standard position, you have to do two things. Two things that this program does automatically every time. The first thing is you have to keep the vertex at the origin. In my program, I can't move the vertex anywhere. The vertex is always at the origin. Okay, so that's the first thing. Second thing, the initial side is always on the positive x-axis. Okay, that's another thing that the program does automatically. I cannot move the initial side. All I can do is move the terminal side. Okay, so there's an angle that's in standard position. And what that does, it just gives us a kind of a uniform way. If I say to sketch a 45-degree angle, everyone's angle would pretty much look the same. Nobody's would be twisted or reflected or upside down. They would all pretty much look like that. Okay, so if I took this and went like that, is that standard position? About right?
No.
No, what's wrong with it?
It's not on the origin.
Right. The initial side is on the positive x-axis, but the vertex isn't at the origin. Now, what if I did something like that? Is that in standard position? No. Now the vertex is at the origin, but the initial side is not on the positive x-axis. The terminal side is on the positive y-axis, but that means nothing. Okay. The initial side has to be just like that. Okay. So any questions on what it means to draw an angle in standard position?
Yeah, let's go to paragraph. Thanks.
All right. So now that we know what an angle is, we know how to draw it, we know the parts of it, and we know the directions when you measure that come out positive and negative, we're going to talk specifically about the units, okay, that we use to measure angles. Okay. So the two units that we use are degrees and radians. You can also describe an angle as a revolution. Right? Like to me, that looks like it's about an eighth of a revolution. Right? If 90 degrees is straight up, that's a quarter of a circle. That's maybe about an eighth of a revolution. So let's start there. How many degrees to make one full revolution?
360.
360. Okay, so if we know that in 360 degrees there is one revolution, that fact would allow us to convert anything we want between degrees and revolutions. Like if you said to me, how many revolutions is 150 degrees? Well, I would just set up a proportion and solve. If 360 degrees is one revolution, 150 is x revolutions. And then we just cross multiply. But the key to doing this is you had to already know that fact. You had to know that in 360 degrees there was one revolution. That was kind of the starting point. Now, what if somebody had said this as a starting point? Is that true? Yeah, that's perfectly fine as a starting point as well. If you use that to solve this problem, you're going to get exactly the same answer. But the key is you've got to have something to start with. You have to already know a connection between a certain amount of degrees and a certain amount of revolutions. Whether you know 360 and 1, 180 and 0.5, 90 and 0.25, it doesn't matter. You just have to know a starting fact. Well, that's going to be our goal to figure out here. Okay, we know one revolution is 360 degrees, but how many radians is that? If we can figure out how many radians are in 360 degrees, that's our starting point. We can use that to figure out anything else you want to know. we've got to figure this out first. How many radians in a revolution? Does anybody already know? Yes, I know. Yeah. Hold that back. But will anybody else familiar? Has anybody used radians before? Okay, so let's start with kind of visualizing what a radian is. I'm not going to describe anything numerical. I'm going to draw a picture and kind of describe it geometrically, okay, what a radian is. Okay, we're going to draw that circle. Inside that circle, I've drawn an angle. I tried to put the vertex of the angle right at the center of the circle. The two rays of the circle I've labeled R. What do you think R stands for? Radian. Radian? Not radian. Think about a line from the center to the circumference.
Radius.
Radius. But if you put that word right below radian, radian, radius, they look very similar. And that's because there's a connection between them. Okay. And I'm going to show you what the connection is between radians and a radius right now. That angle has two rays. Okay. The rays come out from the center. They hit the circumference here and here. Between those two dots, I've drawn an arc, okay, connecting this point to this point. Okay, any questions on the diagram? All right. So, if you were to take a piece of string, or a formula, if you knew one, and somehow measure that arc in red, okay, it's not straight, it's an arc. So if you take a piece of string, measure that arc in red, and then take a ruler and measure the radius that's in black. If they came out exactly the same, then what you have drawn there is a picture of 1 radian. That's how you would draw 1 radian. If somebody said, I want you to sketch me an angle that's exactly 1 radian, you would try to sketch it so that this arc comes out exactly the same size as the radius. If you made the arc too big, well, then your angle would be more than 1 radian. If you made the arc smaller than the radius, then your angle would be less than 1 radian. It doesn't really answer the question how many radians in 360 degrees. All this shows you is how you could physically sketch an angle that's 1 radian. Make the arc size the same as the radius. And that's 1 radian. Yeah?
Now, when you mean distance apart, like can you cut through the circle, that distance, or the circle around the circle?
So when I say length of arc,
Distance around the circle, my bad.
so when I say length of arc, you have to be right on that edge.
Alright, so you can't just cut straight through?
No,
Alright.
no, it's not a straight segment, it's an arc. So if the length of that arc in red matches the radius in black, that's an angle of 1 radian. Okay, any question on that? And that's a somewhat accurate sketch. Like to scale, I would say that looks about right. So that's roughly what a radian would look like, size-wise. Okay, but we want to talk more about numerically. How can we figure out some actual numbers here instead of just ideas? Well, we can't prove everything. Okay, I have to give you something to start with to figure out that question mark. Okay, so the fact that I'm going to give you is this fact. And this says that an angle's measurement in radians, okay, so forget about degrees, an angle's measurement in radians is numerically equal to the length of the corresponding arc on a unit circle. Okay, so we might have to define what unit circle means. So the first thing is a unit circle, it's just a circle. It's a special circle. It's a circle with radius 1. It's all that a unit circle is. It's a circle with a radius of 1. 1 what? 1 foot, 1 inch, doesn't matter. 1 unit. 1 anything. 1 mile, whatever you want it to be. Okay, so another way I can word that is I could say, if you measure an angle in radians, if you measure an angle in radians, then write that number down. And then you measure the length of an arc using a piece of string. And then you write that number down. The two numbers that you just wrote down on this type of circle always come out exactly the same. Okay? So if you measure an angle in radians, it is the same as the arc length. It's exactly the same statement that I have up above. I just kind of paraphrased it a little bit. Okay, so what that means, if I give you an actual example, let's say you measure an angle on a unit circle. And let's say this is 1 inch. And let's say you measure that angle and it comes out to 0.5 radians. That's a pretty small angle, so it's probably a pretty small number. If that angle comes out to 0.5 radians, I guarantee you that arc is 0.5 inches. If that angle is 0.6 radians, that would be 0.6 inches. Okay? The point I'm trying to show you is the size of this angle and the size of this arc are exactly the same on a unit circle. Any question on that idea? Now, if you say, what happens on a circle with radius of 2? Well, it's different. This idea doesn't work. So it has to be a circle with a radius of 1. All right, so now if we can figure out some kind of connection between the size of an angle and the size of the arc, then we can figure out this question mark. So the question mark is to figure out how many radians in 360 degrees. Right? If I was tracing my pencil and I went 360 degrees, how far around the circle would I go? Yeah, 1 full time, right? I go all the way around. Well, instead of figuring out how many radians are in 360 degrees, this just says right here, I could just measure the arc that goes all the way around the circle, and that number will come out exactly the same as how many radians go all the way around the circle. Right? So the angle in radians is the same as the length of the arc. So let's see if we can figure out how big the arc is that goes all the way around the circle. And if you can find that number, that will be exactly the same as that number. The size of the arc that goes all the way around the circle is the size of the number of radians that go all the way around the circle. So what do we call that when you go all the way around the circle? It's the what of the circle? It's the circumference. So now rewording my question a little bit, if I can find the circumference of that circle, that number is exactly the same as the angle that goes all the way around the circle in radians, and that's what I want to know. So what's the formula for the circumference of a circle? Remember? Yep.
2 pi r squared.
Just 2 pi r. So pi r squared is area, 2 pi r circumference. Okay. Now let's find the circumference of this circle. What's the radius that I'm dealing with in my circle? Yep. 1. Dealing with a unit circle. So I get 2 pi times 1, which is just 2 pi. So I just found the circumference of the unit circle, but that is exactly the same as how many radians are in a full revolution. So there are 2 pi radians in 1 revolution. And the only way we can really figure that out is with that fact that the size of the arc and the size of the angle are exactly the same on a unit circle. Okay, without that fact, we would have been kind of stuck. And you might have noticed when I went all the way to 360, if I can get it right on 360, well, notice what it says down below 360, 2 pi. That's because 360 degrees is the same as 2 pi radians. Now, you might notice sometimes the program writes a decimal, like 5.74. Sometimes all of a sudden you see a pi pop up, like 3 pi over 2, and then it goes back to a decimal. Okay, pi, you see that over here? There are certain angles that we usually write as a multiple of pi, and then there are certain angles that we usually, if it's random, we just write the random decimal. I'll explain to you which angles are multiples of pi and which ones are just random decimals. Okay, but once we'll talk about that in a little bit. Okay, so now we know that there's 360 degrees and 2 pi radians. So let's write that down. Now, you could just set up a proportion every time and solve. You could do, I'm not going to do it this way, but you could do 360 degrees over 2 pi. And then if I said to you 12 degrees, how many radians is it? Just 360 is to 2 pi, as 12 is to x, and you could just cross multiply. But we're going to come up with an even easier way. Right, what could I divide each side by here to make these numbers a little smaller? Yeah? You could divide each side by 2. And I could say that 180 degrees, or half a revolution, is pi radians. But usually when you give someone a conversion, there's a certain number in it. 180 usually isn't in it, and neither is pi. Anyone think of the number that's in pretty much every conversion you tell someone? How about, Jordan, can you give me a conversion between anything to anything?
I have no idea.
Use time. Like, say, minutes to seconds.
1 hour is 60 minutes.
Okay. Did I tell you what numbers to say? Or did you just say those?
I just said.
You just said them. I didn't tell you to say anything. He said 1 hour. There's 60 minutes. Is that what you said?
60 minutes, yeah.
60 minutes, okay. All right. Can somebody give me another conversion? Between anything. How about Chris? How about length? Give me something with length.
I don't know.
Think of any two. Name a unit you measure stuff in.
Inches.
Inches. Okay. Name another unit you measure stuff in.
Centimeters.
That's kind of hard. Let's go. How about feet?
Okay, feet.
Yeah. So give me a conversion between inches and feet.
12 inches and 1 foot.
12 inches in 1 foot. Her numbers, not mine. So I didn't tell her to say those. But there's something in common here that everyone just happens to keep saying. Yeah? 1. Usually when you give someone a conversion, if someone just says, give me a conversion, it has a 1 in it. Usually you don't say to someone, how many inches in a foot? You don't say 48 inches in 4 feet. It's true, but usually you just say 1 foot, 12 inches. So we're going to do the same thing here. I want to take that conversion, and I want to get a 1 in it. if you get a 1 on the left, that's going to convert one way between degrees and radians. If you get a 1 on the right, it's going to convert the other way. Let's start by getting a 1 on the left. Okay. What could I do to both sides to make the left-hand side a 1? Yep.
Divide by 180.
Divide by 180. Divide by 180. Now we've got something that's pretty useful. 1 degree equals pi over 180 radians. So now if I said to you, all right, I don't want to know what 1 degree equals, I want to know what 3 degrees equals. If you multiply the left side by 3 and the right side by 3, there's a formula for 3 radians. 3 degrees equals 3 pi over 180. If I said to you, how about anything, 6 degrees, multiply by 6, multiply by 6. There's a formula that would convert 6 degrees to radians. So the key each time is right here. You have pi on top, you divided by 180 in the bottom. So anytime you want to convert from degrees to radians, pi is on top, divided by 180 is on the bottom. Take whatever number it is, 6, 7, 13. If you want to convert 13 degrees to radians, multiply it by pi, divide it by 180. And when we multiply by pi, we don't normally write 3.14, we just leave pi. Okay? Just like this program leaves pi in the answer sometimes. They didn't write 3 times 3.14 divided by 2. They just leave the pi. Okay? Okay, so that's degrees to radians. Let's go back and let's look at the same equation again. Except this time I want to get a 1 on the other side. What would I have to do on both sides to get a 1 on the right? Yep.
Divide by pi.
We'll divide each side by pi. And now we're going to have something pretty useful. We're going to have a conversion that has a 1 in it. Now it says 1 radian, because the pi's cancel, 1 radian equals 180 divided by pi degrees. So if you wanted to know how many degrees exactly is 1 radian, type on your calculator 180 divided by and hit your pi button. It's about 50, it comes out to about 53 something. If you wanted to know a formula for 4 radians, well, multiply by 4, multiply by 4. Now the right-hand side says 4 times 1, that's 4 radians, equals, do out that calculation. So the point in this one is whatever you want to convert from radians to degrees, that's how you do it. You multiply by 180, divide by pi. Those are the 2 steps to convert from radians to degrees. Multiply by 180, and then divide by pi.
What do you mean, multiply by pi?
Multiply by pi and divide by 180, yes. Okay, 180 is in the top, pi is in the bottom. So multiply by 180, divide by pi. So the 2 steps look very similar. If we go back, then I mix them up sometimes. One of them is multiply by 180, divide by pi. The other one is multiply by 180, or divide by 180, multiply by pi. So it's very easy to mix them up. So I'm going to try to show you a way you can remember which one is which. The way to remember which one is which is when you think degrees, if I go back up for a second, when you think degrees, think of the number 180. The 180 has a degree symbol on it. When you think of pi, think radians. Just think those two things and that'll help everything work out. When you think degrees, think 180. When you think radians, think pi. And if you can remember that idea, you don't even really need to remember what I have on the board right now. Okay? Just those two things I just said. Okay, so let's look at converting this from degrees to radians. Okay, so all the problems that we do are going to be one of two ways. It's either pi over 180 or it's 180 over pi. Those are the two things we just wrote down. We've got to keep straight which one is which. Well, the goal here is to convert to radians. So when I'm done, I want this degree symbol to disappear. Think of 60 degrees as a fraction. 60 over 1. Where would the degree symbol have to go in the fraction on the right to cancel out the degree symbol in the fraction on the left? It would have to go in the bottom. Okay, it would have to go in the bottom to cancel out the degree symbol, and that's what you want to do. You want to get rid of the degree symbol and end up with radians. So if degrees is in the bottom, radians is in the top. Now, if you can just remember the two numbers I said to think of, we're all set. When I said degrees, what number do we think of when you think degrees?
180.
That's the 180. And the number with radians? Pi. That's it. Now just do that out. Degrees is gone. Okay, you're left with radians. And I usually reduce 60 and 180 or whatever number it is if I can first. Does 60 go into 180? Yep. How many times? 3. Becomes a 1. Becomes a 3. So your final answer is 1 times pi over 1 times 3. Pi over 3. So 60 degrees is equal to pi over 3 radians. Let's look at it on here and see what happens. So if I put it on 60 degrees, it says pi over 3. Did it put RAD after the pi over 3? No. Did it put a degree symbol after the 60 though? Yes. So normally when you write an answer in radians, you don't put RAD. I did the first time just to get you used to it. That's how you can expect to see the answer written. Just like it is right there. If you want to write an angle in degrees, you absolutely need to put the circle on it. If you want to write an answer in radians, you don't put anything. Okay, let's try this one. 150 degrees. So first thing I figure out is where degrees would go to cancel, and then I can fill in the 180 and the pi in the right spots. So Sam, where would I put degrees to make it cancel out?
On the bottom.
Yep, in the bottom. And if degrees is in the bottom, then what would be in the top?
Pi.
Yep, pi, and we're just going to pretend it's radians. I'm not going to write RAD this time. That's understood, it's invisible. And the number in the bottom would be, yeah, 180. Okay, so degrees cancels out. Final answer is going to have radians. It's invisible. Pretend it's there. What number goes into 150 and 180? There's a lot of numbers, but if we do the biggest one, that's good. Nathan? 30. How many times does 30 go into 150?
5.
Yep. And 180?
6.
6. So you're left with 5 times pi over 6. Okay, let's use the program and let's go to 150 and see how the calculator, or how it displays the answer. Okay, so if I go to 150, it puts it as 5 pi over 6. Does anyone see a pattern with the ones it's writing as fractions with pi versus something it's writing as a decimal? So 150 it wrote as a fraction with pi, and 60 so far. Okay, let's see what those are both multiples of. Yep.
30.
Yeah, in general, angles that are multiples of 30 and angles that are multiples of 45, we write with a fraction with pi. And there's some overlap there. 90 is a multiple of 30 and 45. Okay. So that's generally in the book, if you see angles that are multiples of 30 and 45, you're going to leave it as a fraction with pi. Okay, try this one. Okay, try that one on your own. There's no difference here other than when you're done your final answer, you throw a negative in front of the answer. But you do it the same way. All right, let's take a look and see how we did on this one. How about Emma? What did you multiply by to convert from degrees to radians?
I did negative 45 over 1.
Yep.
I did 5 over 180.
Perfect.
Then I divided them first both by 5.
Okay.
And then I noticed that they could be divided by 9.
Okay, so if you can divide by 5 and 9, you can divide by the product of them, which is 45. So I'll just do it in one step. So 45 goes in once, 4, and what did you get for a final answer?
I got negative pi over 4.
Perfect. Negative pi over 4. Notice if you check it on the calculator, let's see, negative 45, doesn't write it as a decimal, negative pi over 4. 90, I'm going to skip over that one. If you wanted to do it, that would be pi over 2. If you want to try it and practice later. At this point, because I mean, once you do trig a lot, most of the 30s and 45s you have memorized. If somebody would ask me what is 107 in radians, I have no idea. To 2 decimal places off the top of my head, I need a calculator. So if it's a random angle like 107, we'll round to 2 decimal places. Okay, so it's still the same steps. Multiply by pi. You got to put the 180 in the bottom so it cancels out. And there's no point to even thinking about reducing because you're just going to type it in and round it off anyway. Okay. Only thing you want to be careful about when you type it in is don't use the pi button. Don't use 3.14. Use the pi button. Why use the pi button? What's the difference? Nathan?
It's a lot more precise than 3.14.
Yeah, there's a lot more digits there, so it's more accurate. So 107 times pi divided by 180, we get about 1.87. And what is that? That's 1.87 what? Radians? Do I need to write the word radians? What do you think? How about Cassandra? Do I write radians after that? No. Okay, when it's in radians, you just leave it. And people know if you're talking about angles and trig and you don't put a label, it's radians. It's kind of like in algebra. People know that there's a 1 in front of that x if you don't put it. People just know. Okay? All right, so last thing is converting the other way. Basically, same idea. Just we're going to flip our fraction. In the first one, I'm going to write radians. After this, though, I'm going to stop writing. Okay, so we have pi over 6. So Ben, I've got radians in the top. Where would radians have to go in this fraction to cancel out? Well, if you put radians in the top, then you'd have radians times radians, which would be radians squared. So it'd have to go on the bottom to cancel out. which means what unit would be in the top instead? Think about we're converting between radians and degrees. Okay. So let's fill in what we've got. So when you think degrees, think 180. You think radians, think pi. What's going to cancel out here? Yep, radians cancels. What else?
Pi.
The pi's. So all you're left with is 180 divided by 6. And 180 divided by 6 would give me 30. And notice I put the degree symbol on it, and I have to. If I left the degree symbol off, what's that answer?
30 radians.
That's 30 radians. That's 30 degrees. Any questions on that one? All right. Okay, why don't you guys try that one on your own. See if you can convert 3 pi over 2 radians to degrees. Okay, so we'll do one like that. And then if people feel pretty good with these, we'll do the last one, which is a decimal. And then that'll be it. Okay, so let's take a look and see how we did. Pacey, can you walk me through what I need to do here?
So you would multiply by 180 divided by pi.
Yep. Multiply by 180, divide by pi. Okay.
The pi's cancel.
Yep. Pi's cancel and radians cancel. It's invisible, but we'll just pretend that we canceled it.
And then before I solved it, I divided the 180 by 2 into 90 to make it easier.
All right.
And
Sounds good.
Multiply by 3.
Okay. So you're left with 3 times 90 with a degree symbol, which is how much?
270 degrees.
270 degrees. Yep. Okay. Any questions on that one? Okay. Anyone feel like they need to do another one that's this type? Okay. So let's look at. If you wanted to do that one, it would be negative 135. If you want to check on your own later. But let's do this one. So 3. And again, we got to get used to not seeing RAD. So directions are the same, convert to degrees, but I'm going to add an extra step. Round to 2 decimals. Okay, so we still do the same step. Multiply by 180, divide by pi. If you want to write radians yourself, you can, so you understand. You had radians in the top, if you think of 3 as a fraction. Radians goes next to pi in the bottom. Radians just canceled. This time, though, the pi's don't cancel because there is no other pi. So we just have to type that all in and see what we get. So we've got 3 times 180, that's 540. And then 540 divided by pi. I get 171.89. And remember, we're changing to degrees, so put that symbol. Now, let's say you didn't use the pi button. Let me show you what happens. So 3 times 180 is 540, divided by 3.14. Now, if I'm asking you to round to 2 decimal places, that's quite a bit off. It's 88 versus 97. Right? So to 2 decimal places, now we've lost a lot of accuracy. Right? So always use the pi button. Okay. Any questions on that one? All right. Okay, so homework tonight, it's on page 99. It's 36 through 68, just the evens. We've got about 10 minutes left. take a little bit of time to start it. Okay, those that weren't here yesterday, I'll come talk to you and get you everything you need.